Hello. Yeah. Hi. I'm happy that you're here, and I'm going to talk about cellular automata. Just let's check out who of you knows Game of Life. Okay, we can work with this. So, what can you expect from today? First of all, I'll give you some introduction to cellular automata, the formal model. Then I want to give you a demo of the software that I want to present, Evocell. Many different cellular automata and how to play around with them and mutate them, evolve them. Then I want to talk about artificial life in cellular automata, automata, I've been told, sorry. Yeah, and then I will sum up what we've heard. So, what is a cellular automata? It was introduced by von Neumann and Stanislav Ulam in the 40s, I think. So the father of our computers is also the father of cellular automata. And at this URL, you can find a very interesting paper from that time, if you're interested. It's a mathematical model for a dynamical system that is discrete in time and discrete in space. You will see what this means later. And the dynamical system, it depends only on local interactions. But the interesting thing is that global phenomena emerge out of this local interaction. So, the elements of a cellular automata. Yeah, some regular lattice of cells. It could be a different lattice, but it has to be regular. And at each of these discrete time steps, each cell is in one of S different states. And of course, normally we code the colors, we code the states with colors so that it's easier to visualize. And then the state of each cell at time step t plus 1 is a function of some of its surrounding cells at the previous time step. So yeah, imagine it like this. The sum of the neighboring cells, they influence what the state of the center cell will be in the next time step. And each cell has the same relative neighborhood, so the same neighboring cells. And normally the center cell also influences which state it will have in the next state. So the center cell is also in the neighborhood. This could be confusing otherwise. Because normally you wouldn't think of the center cell as a neighbor of itself. Yeah, typical neighborhoods we will see the von Neumann neighborhood that was used in the first cellular automata that he introduced in the 40s. And then the Moore neighborhood you all know from Game of Life. Yeah, but we could also make the neighborhood bigger so that more cells influence the state at the next time step. Yeah, and how is this influence really modeled? Think about it. For each possible combination of states in the neighboring cells, you have one target cell that the center cell target states the center cell develops into. And this is simply implemented as a lookup table. An example, let's take the Moore neighborhood with 3 states. Then for each possible neighborhood, we have one target. We have one target state. Yeah, this summarizes what I've said so far. And now we can we can ask ourselves the question, how many different cellular automata exist that are like this? And we just, this is a problem. We can just split it in 2 parts, and First, let's ask us how many different neighborhoods do exist. And yeah, each of the n cells in the neighborhood can be in one of S states. Here's an example. So this can be in one of S states, this can be in one of S states, and this two, and this two, and this two. So there are S times S times S, S to the nth power, different neighborhoods. It's analogous to numbering systems with the base S. So it's easy to calculate. So for each of these S to the nth power neighborhood, we have to assign one target state. So if everything is 0, we have to assign one target state. If the center cell is 1 and everything else is 0, or if it's 2. And for each combination till every state is S minus 1. We have to assign one of S target states. So completely analogous to how we calculated the numbers of neighborhoods, we get there are S to the nth power different possible cellular automata. And this is a huge number. And the question is, how do we find the interesting cellular automata in this huge space of possible cellular automata? Here's an idea. We could evolve them. This is an algorithm I would propose. We start with some initial rule, and then we make some copies of this initial rule and just change some entries in the transition function table that I've talked about before. And then we initialize the original cellular automata and the mutated cellular automata with some predefined or random cell pattern, but each with the same cell pattern. Because then differences in the transition function will be seen as differences in the development of the cell pattern. I will demonstrate it shortly. And then we just select the most interesting CA and go back to the start. This can be iterated, of course. And before I show you the demo, I want to talk about symmetries, because if you think about this transition function, then yeah, for example, if I have in the lookup table, I have this entry. So when in the top left corner there's a 0, everything is 0, and these states 1, 2, 3, then I want the center cell to be a 2 in the next time step. Normally, in Game of Life, for example, the transition function is symmetric. That means if I have this entry, I will also have these entries. These are just the rotated versions of the same, rotated by 90 degrees each. Usually the rules I will show you will have this property. They are symmetric. And the interesting part about the symmetric rule, if you start with a symmetric pattern and you have a symmetric rule, it will always stay symmetric over time. And this is rotational symmetry. You can have the same with mirror symmetry, for example. So this would be the mirrored version of the same transition rule. Okay, let's have a look at this in action. Yeah, perfect. So you see the cells here, and to start with, I thought about we just take some patterns you might already know. And you know, Conway, the inventor of Game of Life, he had to simulate the cellular automata on a Go board. And John von Neumann, he couldn't even simulate it on a Go board, he just mathematically proved that it would work. But today, of course, the computer calculates it for us. So Let's have a look at it. Yeah, it's the glider we all know from Game of Life. Most of the time, I don't want to draw the pattern myself. I just want some random cell chunk that I want to see how it evolves. So this can be done easily, like this. So, but I promised you new cell automata, not the old ones you already know. So let's create something new. First of all, I have to define a neighborhood, of course. I have to tell him which cells influence the next state. I'll start with the traditional Moore neighborhood. So this is the center cell, and all these cells influence it. And I start with 4 states, as you can see here. I create this. Now I have it here. So what happens if I'll switch to another color scheme so you can see it better. Oh, it's bad. Okay. So I just initialize it with some random pattern, and what happens if I now calculate one time step? Everything goes to 0, because in the beginning, each neighborhood goes to 0. I have to change some rules. How do you do that? Select it. Here, this is now again a picture of the neighborhood. And this is similar to regular expressions, really. All these question marks mean I don't care what state is here and here and here and here. But I want the center cell to develop into, for example, n0 minus 1. n0 means is the zeroth neighbor. This is this one. n1 is this, n2, n3. So these are the neighbors. And I just say, I don't care what the neighborhood looks like. I just want the center cell to develop into the state it was before, minus 1. So it will decrease in the state. And when it's 0, it doesn't switch to minus 1 because this is not a well-defined state. It stays at 0. And I want to change all the rules that match to this pattern. I could also just change, for example, 500 rules that match this pattern. But I want to change all the rules that matches. And now I mutate it, and let's initialize it, and step. Yeah, everything decreases one state, as I told it to be, of course. Now this is a more interesting rule, but it's still rather boring. So let's make more cell automata. Just well, and now I have 4 of them, and this one is the first. This still has the rule I just initialized. And now just let's do some mutation. But I don't want to mutate it randomly. I want to mutate only specific rules. Rules that match this pattern. Well, so I only want to mutate rules that have zeros here. And I don't care what's down here or here or here. But I want the center cell to develop into the third neighbor. The third neighbor, it's this one here. So this one, it grows out. And let's say I want to mutate 20 entries in the rule table, and I want to have rotational symmetry because it just looks nicer like this. Okay, let's mutate it. Let's look at how it develops. Oh, interesting. Because, of course, the rules that I've defined here, zeros here and any state here, they match for here on the border of this pattern. For example, it matches, and now now the states they grow out, and and then slowly fade out, because most of the rules are still just this fading out. So it's really easy to create all sorts of gliders by these simple mutation rules. By the way, if I click here, then it takes the rule that is in here and produces a mutated copy here and here and here. So just so you know what happens. And it gets initialized with the same cell pattern everywhere. But the development over time is of course different because the rules are different. Yeah. And then when we have found some interesting rules, for example, I say, oh, this looks interesting, then we can continue with this one. Look what it does. Well, you can sit in front of it forever, but let me show you some rules I've already created in this fashion, and we can continue there. Yeah, like, yeah, you can easily get fractal growth phenomena with it, because things that look similar to this, for example. And that's quite easy. How do you create stuff like this? I'll show you. I take 4 cellular automata now, and I'll start with another initial rule. Simply, no matter what state the neighbors have, I want the center cell to stay the same. So I just tell it, yeah, stay the same, stay N0. And I generate all the rules for this. I put it here. And now it will just be static, just stays the same. And if I now add similar rules to the last one, for example, then I change 30 entries. You get this growth phenomena. Let's take a different. So these fractals, they merge very easily, really. Okay. Then I want to show you some cellular automata that really do some computation in this world, but that have been evolved just with the techniques I showed you so far. This one is very interesting. Okay. What does it do? Let's just follow one of these elements here. I'll just take one. And let's watch it. So it just moves, and after it deposits one of these things, and what happens when it touches the next one? Okay, now it just died. That was not exactly what I wanted to show, because it really depends on how many cells there are. Because of course, when it exits on the right side, it comes the right neighbor of these cells is of course are these cells, and it's a torus topology, like you exit on one side, you come in on the other side. And it's very dependent, the behavior of these things depends on exactly how many, like the gliders in Game of Life, depending on in which state the gliders are when they collide, they can either cancel each other out or they form a block or something like this. It's the same here. And what I really wanted to show, they form automatically, so let's just start with some random pattern. Let's watch this here. Yeah. Okay, now they're... Let's work with this. Let's watch this. What happens now if it collides here? Ah, it's the same, boring. Okay, just in case this would happen, I have some predefined patterns. For example, this. So let's just watch it here, and you will notice what it does. Especially watch this region. Yeah, it's a binary counter. It's a decreasing binary counter. If you just interpret the presence of one of these things here as a 0 or a 1, and the absence as the other thing, it just calculates, counts down. And this rule, it has just been created by the techniques I've shown you so far, and it's really amazing what kind of machines come out of it, just by playing around like this. Yeah. Other rules. I'll just give you a show of some of the interesting rules. Oh. All these can be created quite easily. And also sometimes you get some patterns like this, or rules like this, and you notice that it behaves interesting. That's really too dark. Okay. Let's watch it, yeah. This thing is interesting. It grows and it throws out these little gliders on the side. And if I put some of these cells here, then watch what happens. It returns. And now I just put some here. I just copy it. Oh, bad idea. So. Yeah, just goes around forever. And also this deposit here. And I guess it would be possible in this automata or in the last one to construct a Turing machine, although I haven't tried it at this time. But you see, many cellular automata have some computational capacity that you can use. Of course, there are many rules that have gliders of some sort, like this. And sometimes the gliders have also interesting behavior, like they can interact with each other. Show you another rule. Like in this rule. Sometimes when they come near to each other, they just change direction here. Let's watch this region here, for example. Yeah, here they change direction, move upwards. So, but it's of course it's just the behavior of the gliders. It's just created by the local interactions we've seen earlier. There's no other rules except the ones I've already told you about. So you say, okay, interesting effects, but I don't know if you can really create artificial life in cellular automata with this. But as a proof that you can, I want to show you some rule that's not mine, but it's from a Japanese researcher called Hiroki Isayama. It's called the Evo loop, and it's a rule. I'll just load the rule. And it comes with a pattern, with an initial pattern. Let's start with this. Okay, the screen resolution is too low. That's bad. Well. Okay, I'll just copy it from here. And just let's have a look what this pattern does. Let's change the colors. It's a replicator, it makes copies of itself, but it makes the copies according to a plan. Look at these states here, the white and the green ones, and look at how the white states extend this border of the loop. Each white cell, it lets the loop grow for 1 pixel. And now watch at what the green cells do. They introduce a turn. And the interesting thing is that this information, the white and the green states, they always circulate in the circulate through the loop all the time, and at this junction here, it gets copied, like DNA has to be copied at some time. And one copy, it goes out to create the new loop, and the other copy, it just stays in the loop. And if we also watch it carefully, we will see that the information that circles around here, it codes for one side of the loop. So it's actually a fractal built out of, it codes for one side of the loop, including the turn. So the whole loop is made up by four exact copies of the same material. Like DNA has to code in a fractal manner. You can't encode all the information of how a person looks like in the DNA. You can just have a compressed version of it in it. So these loops, they have a compressed version of the information that is needed to build themselves up. And now the screen it's too small. There are now cells that are not visible, but I'm afraid I can't change it now. But watch what happens when sometimes the loops collide. When the loops collide, there come into existence some combinations of states in the neighborhoods that might, for example, change the information that flows through the loop, or it might also lead to a combination that is considered invalid by the rules, and then this magenta state emerges, which really dissolves the loop, like you see it here. Because it dissolves the loop to make space for other loops that still function. So all the loops that don't work anymore, they dissolve themselves to make space for other loops. And sometimes the loops mutate. This one is smaller now, if you look carefully. This is smaller and has a different shape than this one, for example. And then the mutated versions make copies of themselves, of course. And here we see a problem. This loop, the offsprings of this loop, they get smaller by one cell at each time. So eventually, these loops will get smaller and smaller, and so small that they can't really reproduce anymore. So this has a genetic defect, you could say. So from time to time, you will get smaller loops that are able to reproduce. And because the loops are smaller, they can reproduce faster, and eventually the whole space is conquered by the smaller loops. But it really takes some time, and I don't want to waste all the time just here waiting for it. So I'll load a pattern that shows this phenomenon. Yeah, here the loops have already grown very small, and all the big loops don't exist anymore because they died out. Yes. So, as you can see, this cellular automata, it shows evolutionary effects. Although it's really only local rules and local interaction, but it has really some interesting phenomena. And now we can also, where is it? Reanimate there. I want to show some effects. Let's have a look at these loops. They don't do anything because, I'll just zoom in so we can see it better. Oh, sorry, the wrong one. Okay, we can work with this. Too fast. these loops, they don't do anything because they've lost an essential state that's important for growth. And I'll reintroduce it. I'll use some kind of gene therapy here so that it can regain this behavior. I just have to put the red state here and watch what it does. It just sits around, but then it travels along with the black state. And here, when the green states come along, it introduces a new, it grows out of here. Now, perfect, the loop, it works again. It's got smaller, 1 pixel, but let's see if the next generation does the same mistake. No, it works. These loops, they can successfully reproduce and will also conquer the whole space in some time. So we can experiment with these loops a little bit, and for example, we can say, I want it what happens if I introduce 2 red states, for example? Just fix this here. I put one here, like before. No, not here. This is bad. One here. And I'll put another one here. Let's watch it. Of course, it makes 2 copies of itself. It's the same thing, really. So, what can you do with this? You can genetically engineer the loops if you want. I'll load another pattern. It's the Sony version of the Evo loop, because Sony thought, well, Evo loops, they reproduce by themselves, we can make money with it. Let's just make our own version of it and sell it. Yeah, no, it doesn't contain a rootkit, but it contains digital rights management, as I will show you. So we have it here. We now know what the states mean. This one is red. Here's a red one. Here's a red one. So there will be a lot of loops growing, and just look what it does. It's an Evo loop, so it makes copies of itself, like Sony promised us. And it even makes 4 copies of it. Let's make it faster. Works just fine. But now they've introduced some self-destruction. And eventually you don't have anything left, but it worked once. Thanks. So, yeah, one other interesting phenomenon is, as I said, the Evo loop, it was created by hand by a scientist. But what happens if we just mutate the rules for the Evo loop? And I have some mutations here. This one is very interesting, I think. Just start with some random noise and see how it grows. Okay. Let's make it more clear. Just draw some state here. Watch this. Yeah, it's the ubiquitous Sierpinski triangle, but I'm sure you know that it's easy to produce these patterns with cellular automata. And so it's not a wonder that they pop up all the time because I have many of these rules. For example, this one is also Sierpinski triangle. Yeah, it's a nicer one, actually. Makes all sorts of triangles. Like this. And we can also take this rule and continue from here, make mutations of this one. So I select it. As you can see, this one, it has a different neighborhood. Then it has this von Neumann neighborhood. And let's just make some random changes. Look what it does. With this setting here, I can change how many entries in the transition rule I want to change. Now let's take some more. Okay, it gets too active. This one looks interesting. Now it's a strange Sierpinski triangle. Let's just take and look how it develops. It is just somehow disturbed. Okay. What else can I show you? Which exact rule is used? Oh, I don't know, really. I mean, I can, of course, look at the rules, but normally you don't know what each rule does. That's because the space of, there are so many different rules. It would be very hard to create them by hand. So I want to use these mutation rules and this regular expression stuff to automatically generate interesting mutations, and then I select it. And of course, I plan to introduce some automatic features that automatically detect interesting rules, but this isn't done at the moment. Want to show you another glider with a completely different, oops. Oh, this is the wrong one. Yeah. With a completely different neighborhood. This is the neighborhood. And there are some interesting phenomena happens. We have them here. Need some more. I'll just copy this one. Okay. The mutation I loaded is one that it's not very active. So I'll just take one that's more active, where more gliders emerge. But of course, they are related to each other. This is a mutation of the last rule. And here, sometimes the gliders can pass through each other. I hope this works now. Let's watch this. They just pass through each other because the neighborhood is like this. They don't influence each other. All kind of interesting things happen. Okay. So I think you have an idea what you can do with the software, and I'll continue with the slides. This was the demo. Okay, I've told you about this. I've told you about the Evo loop. If you're interested in it, go to this URL, then you'll find all the information about it. It is a self-replicating structure with DNA inside the loop. DNA is copies, we had this already. Yeah, we had this already, but I want to come back to the theme artificial life in cellular automata. Because what generally is interesting about it is that everything about the loops that we've seen and all the other rules, it's, as I said before, it's the result of only local rules, because it only looks at local rules. You could parallelize this calculation, for example, very easily, because you don't need global information to calculate the next state of each cell. And it shows evolution without such things as a concept of individuals. So normally, when you do genetic algorithms, you have something like, you have an object that represents individuals, and then you have something like a fitness function, for example, that gives each individual a fitness, and then you select the n fittest individuals and mutate them somehow, and you go to the next round. All this wasn't here in the Evo loops. There was no concept of an individual loop. It was just a pattern of cells. But for us as observers, it looked like an individual loop. But it's not an entity in the program. And it's like ourselves, for example. We consist of atoms. And I don't think there's a program running that chooses the fittest humans and mutates them. No, it's just happening by local interactions of molecules with each other. So this is the closest, I think, the closest to artificial life we really have, because there we don't need this concept of a fitness function or concept of individuals or hard-coded genetic algorithms. It all happens out of the inner dynamics of the system. Yeah, and the Evo loop rule I've showed you, it's an existence proof of artificial life in cellular automata, because I've already calculated how many rules there exist for some neighborhoods and some number of states. This is a huge number. And by showing the Evo loop, I've shown you one point in this huge space. And I've proven that there is at least one interesting point in this space. So by using evolution or other things I demonstrated, one could explore this space and maybe find much more interesting rules. And that's what the software really is written for. Because I haven't seen such software before. That's why I started it. So that brings me to the end. Yeah, I say it again. There's a huge space of possible cellular automata. I've presented some tools for exploring this space. And I gave some existence proofs that there are some interesting points in this space. And I hope I got you interested in cellular automata again. And if you're interested in the software, you can, of course, get it here, source code included, with all rights on your side. Yeah, that's it. Are there any questions? Yeah? He asked if I've done anything in more than 2 dimensions. The engine, so the classes that are behind this, it supports arbitrary neighborhoods, arbitrary dimensions, and everything like this. But the user interface only supports 2-dimensional stuff. And it would be a problem for visualization. But the classes that are behind it are really abstract. They can do anything. And I've tried it once in 3D, but I didn't have any visualization code, so it was awkward.
Is there any work
Yeah, if you Google for 3D and cellular automata, you'll find some things. Yeah. It would be very interesting, really, to do this. Yeah. Anything else? Yeah.
I have a question about the Evoloop. You mentioned that it was created on purpose by this researcher. And how many rules does this Evoloop consist of?
It's about 500 rules, but with symmetries and all this, it gets more. But about decent. Then there are many default rules. So for most of the states, it just dies. This test state develops, so it dissolves everything again. Yeah, 500 rules and some more because there's symmetries and stuff like that. But
and can one say if this is the minimal set of rules? So are there any rules which you don't need also?
It's very hard to prove such things mathematically. I don't know if you can say this, but I can tell you something about the history of the Evoloop, because it really goes back to John von Neumann. John von Neumann had this idea. Why did he invent cellular automata? Because he wondered why living things can reproduce without degenerating, or even get better with time. And so he designed this cellular automata with 29 states. And it is really a machine. If you see it, I tried to, there's an open source implementation for the automata John von Neumann created, but it has some weird self-written compressed file scheme, and so I wasn't able for today to extract the rule out of there and load it into my program. Otherwise, I would have shown it to you, but you can find it on the internet. It's really a huge cellular machine that has some cellular tape where it reads states out and constructs another machine according to the information on the tape. Then there's a second machine that can copy tapes. And so you have a tape for the machine that can create another machine out of a tape. And you have a tape for this machine and a tape for the tape copier. And then the tape copier also copies the tapes. And then you get reproduction. Perfect. And interesting, von Neumann didn't see any computer simulations of it. He just showed it mathematically that it works. And today there are simulations, but he died way too early to ever see it. And some small parts of this cellular machine, they are similar to the loop. They are similar to the Evoloop. And Christopher Langton, I don't know if he's an artificial life researcher, he just took the rules that are needed for this loop and made a self-replicating structure out of it. But the problem with this loop from Christopher Langton, it was that in the paper he published, he didn't define many possible states. And so nobody knew what to do with them. And usually you just did something, and then eventually the loops just crashed into each other and became dysfunctional. And so then this Japanese guy came along and said, we need some way to clean the space up again. And he added some states and some transitions to do this. And that's where it is now. But I don't know if probably it could be done with lesser states, with different neighborhoods. But it's hard to find the optimal solution to this, or to prove something like this. Yeah?
You can create
you can create any Turing machine, yeah?
Self-reproducing machine. So what for do you need 500 rules if you can do the same with 3 rules?
This goes, first of all, because I think it's interesting in itself, although, and then a Turing machine is not everything, because of course you can create Turing machines with game of life, and I've seen game of life patterns that calculate prime numbers or stuff like this. But if you just start with a random game of life pattern, you won't get anything interesting. And the binary counter we've seen, the decreasing binary counter, it just forms out of random data. I loaded a pattern now because I didn't want to sit here 10 minutes doing random initialization and waiting for an interesting pattern to emerge, but it gets into existence just by itself, just by creating random chunk. And because this is also what we are, I mean, living things. There's no creator that creates initial pattern, I think. And so it has to form out of random stuff. And I'm trying to look for cellular automata that form out of random patterns. Cellular automata?
Who created the rules for the cellular automata which works on the random state?
You mean in the universe or here? I don't know.
It's the same problem delegated to a different level. So.
You're right, yeah. I don't want to discuss this now, but maybe later. Okay. Other questions? No.
Yeah.
Just go. Yeah.
Yeah, just. The Evolup rule set was clearly designed by a scientist, but the rule set for your binary counter, did you design it or did it occur just by mutation?
It was by mutation. I can show you some precessors because I saved the rules along when I designed the rules, so I could show it to you. So this was the original Gardner, as I called it then. Yeah, and it looked like this. I don't know how I got to this, but I just started with some initial rules and mutated along. So this was this rule. It looked interesting, and then I made this by mutation. But here now everything died out. So I made it more active by adding random rules, basically. And then it got the ones I showed you. This was the rule that produces the binary counters. As you can see here, now here there are binary counters, totally out of random data. For example, here's a mutation of this again. Okay, so this was really created with mutation, not designed in any way. Okay. There was another question?